Well, I'll get started. Let me begin with a word of prayer. So, Dearly Father, we thank you for this day. Again, I thank you for this class, for these students. Just ask you to bless our work today. Help us just to understand a little bit more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. So today, I'll talk to you guys about gravitation. And so, the fundamental thing is Newton's universal law of gravitation, which, let me show you how it works. So, if we have some coordinate system, all right, so here's my coordinate system, and suppose I have mass m1 up here, and it's at position vector r1, all right, and then I've got mass 2, I guess I'll put it down here, like that, right, and it's at position vector r2, right, then the force of gravity is attractive, and each of the masses produces gravity, and the gravity pulls one mass on the other and the other on the one. In particular, we can talk about the force of gravity on M2. So it's along the line that connects them. All right. So the force of gravity on M2, I'll draw a picture of it. It's attractive like this. So this is on M2 due to M1. All right? And what's the formula for this? Well, the formula for this is as follows. The force of gravity, like I just said, on M2 due to M1 is equal to minus big G M1 M2 divided by, let's call it, let me stick with my notation here, script R2 minus R1, the length of that squared times the unit vector of that guy. So, or if you like, I could introduce another symbol and write it this way. So what we got is minus G M1 M2 script R hat divided by script R squared. It's inverse reciprocal. So, like this right here, I believe would be script R hat. So R2 minus R1 points what direction? Let's make sure I don't have a sign error. I mean, it's possible, right? So, where is R2 minus R1 in this picture, guys? So I'm saying that script R is equal to R2 minus R1, right? So that means that R2, allegedly, is equal to script R vector plus R1. So if you want to envision that, yeah. See, so like this is R1, right? And then this is, this vector like that is script R. So script R vector goes from M1 to M2 like that. So it goes in that direction. I put a minus in the formula because gravity is attractive. Are we understanding? So this is how we have to calculate the force of gravity of one mass on another. You know, if they're at like arbitrary points, this gives you the direction of the force and everything. Now, oftentimes, we like to think about one of the masses being at the origin And then things get a little bit easier in terms of the formula, right? Like, so example 1, I have the situation that the mass is at the origin. I'll put M1 at the origin, all right? And in fact, I'll even make it big. So, well, I'll tell you, I won't make it big just yet. I'll put M1 at the origin, all right? And in that situation, if M2 is out here, right, then the position vector R2, we don't really need, we don't need R1 and R2 at this point, right? So like, in this case, R1 equals to the origin, and we can just let R2 be the position vector of the mass, second mass, right? So in that situation, the formula, a little bit easier. The force of gravity is just equal to minus g m1 m2 divided by r squared r hat, right? Where r hat is just the, you know, unit vector that points out from the origin, like so. Any questions? Now this g here is an astronomically small number. Experiment reveals that this g, it's one of the most precisely known physical constants, but here's what it is. Big G is equal to 6.67 excuse me, 259 times 10 to the minus 11 Newton meters squared per kilogram. So this is the universal gravitational constant. It is not the little g, which is of course 9.8 or 9.81, depending on how you want to think about it. All right. So, all right, let's go on here. Let's talk about example 1 a little bit more. I'll call it example 2 actually. So suppose that your mass is not like a point mass, right? Like I'm imagining the mass is small. What's the situation if the mass is larger? If the mass is larger, the way that gravity works is it's as if it's a point mass at its center of mass, assuming that there's like spherical symmetry and such. So to a good approximation, the Earth is a sphere, right? And the radius of the Earth is r sub e. So if you put a mass here, excuse me, surface of the Earth, you know, I'm neglecting the size of the mass if you don't mind. So here's my, I just have to, I mean, let me draw it big, but I don't care about the size of the little m, right? So in this situation, the force of gravity is, you know, minus g, the little mass, times the mass of the Earth, divided by the radius of the Earth squared, right? And we could put a y hat here if you like. If you want to call y the, you know, direction that goes vertically up from the Earth. Of course, you could put an r hat there if you like. So then, what's the situation here? So, the mass of the Earth, I'll tell you what that is, you guys. So the mass of the Earth, it actually is about approximately 5.98 times 10 to the 24th kilograms. And the radius of the Earth, I don't remember right offhand. Can we figure that out? Let's figure out what the radius of the Earth must be. See, what's the situation here? If we're near the surface of the Earth, we already have a force for gravity. What is it? What have we been saying the force of gravity is all along? It's what? Minus mg y hat, right? This, right? From like early in this course, we've been doing that. So we know what little g is, right? So we could figure out, if we know two of these things, if we know the mass of the Earth and we know the universal gravitational constant, we can estimate the radius of the Earth if we understand this formula, right? Let's work it out. What is the radius of the Earth then? Given what we know here. So, goodness gracious. we've got g little m, mass of the Earth, divided by the radius of the Earth squared, is equal to little mg. So this tells me that the radius of the Earth squared is equal to g times the mass of the Earth divided by little g. Am I right? The m's cancel, right? Gravity is the same whether or not you go on a diet. And anyway, see here. So I think I got everything. So work it out. You guys help me out here. So we got I need glasses. 6.67259. I'm going to stop us after 6.673 because we don't have that many digits on the little g. Times 10 to the minus 11 times 5.94 times 10 to the 24, right? Divided by, let's say, 9.8 meters per second squared. What are the units up here? The universal gravitational constant has units of Newton meters squared per kilogram. So we've got ourselves Newton meters squared per kilogram, and then we got the kilogram from the mass of the Earth. Kilograms, they be canceling. The mass, goodness gracious. What else we got here? Yeah.
You said I was 9.98 and
Oh no. Oops. I wonder which one's right. Quick, somebody go weigh the Earth. Well, if we believe my notes, 5.98. All right, so let's work this out. What do we got? So if you don't know how to do scientific notation on your calculator, you're going to need to learn, right? Because all of these kind of calculations involve large powers of 10. I guess you could do it by algebra if you wanted. 10 to the minus 11. We got here times 5.9. Actually, the way I like to do these is not to do, the way I do this, guys, is I multiply the numbers. And I do the x, oh, come on, stupid calculator. I multiply the numbers, I do the arithmetic, the powers of 10 directly. That's probably a better way. So 6.673 times 5.98 divided by 9.8, that gives me 4.072, let's say, times 10 to the what? Check it out. You got 24 minus 11, also known as 13, is that right? And I believe after the dust settles here, what's a Newton? Kilogram meter per second squared, right? So if you think about that, we've got a net, like we got meters, we have a meters cubed, What?
You have meters squared in units, which matches because you have the radius squared on the other side.
Yeah, it seems like I've got an extra kilogram.
No, you don't.
They cancel?
You should have that on the.
But there's a kilogram in the Newton.
Yeah, it's the constants in Newton meters squared per kilogram squared, I believe.
Yeah, I'm not sure I believe my units for G. Do you guys believe my units for G? I don't believe the units for G. Why? Why do you not believe? Let's hope I copied it down wrong. Oh no, error in the notes. Lecture 31's got a mistake. That cannot be kilogram alone on its lonesome. If we put this into the formula, we've got the big G times the mass divided by a distance squared, right? This is a unit vector. It's dimensionless. So we should get newtons, it's a force. But we don't unless we take that kilogram and square it. We need a kilogram squared there because we're multiplying G by a mass times a mass, which is kilogram squared, right? So it should be kilogram squared. Excuse me. the kilogram squared is good, then that cancels, and you're absolutely right. We get a net of meters squared here, which we should hope for. All right. I'm glad I checked. Otherwise, I might have been, I might have sent you off on your way with an incorrect units for the big G. That would be no good. Okay, so then what? Take the square root. What do we get? Radius of the Earth is approximately what? Let's see here, times 10 to the 13. All right, square root that thing. Ooh, well, I got to count the number. 1, 2, 3, 4, 5, 6. So 6.381. 6.381 times 10 to the what? 10 to the 6th meters, aka about 6,381 kilometers, radius of the Earth. So a little over 6,000 kilometers. If we divide that by what is how many meters in a mile? 1,600. 1,609, I think. So that's just shy of 4,000 miles. So it's close to 4,000 miles. That's the radius of the Earth. If the radius of the Earth is 4,000 miles, what's the circumference? So you got about, that implies 2 pi r times the radius of the Earth is round about 24,900 miles. So if you want to make a race, well, never mind. You can race all the way around the Earth, right? Any questions? All right. So is gravity a conservative force? What do you guys think? I mean, I hope so, right? So it is. And we can talk more about the gravitational potential energy, and we will. But the next thing on my list of things to do is to talk about Kepler's law. Do you guys know what Kepler's law is? Well, you should say which one, right? I think there are 3 laws of Kepler. But the one I'm interested in particular is the one that states that the square of the period of the orbit is proportional to the cube of the radius of the orbit. And I want to work that out here. So, so Kepler observed these things, right, from data that was collected by this dude named Tycho Brahe. And so here's a picture of the sun, very realistic, and here's the Earth, all right? And what does that do? What's the sun do? What's the Earth do? So I'm sorry if you're a flat earther, then you'll just have to come back another semester, I guess. I don't know. I've got nothing for you. Because we're going to assume that the Earth moves and the sun is at the center of the orbit for the Earth, right? This is the heliocentric model. It's been around since about Copernicus time. That's about 1590, something like that. But what makes the Earth, rotate, travel around the sun is what? The force of gravity of the sun is what we think. So if the Earth, and so to a good approximation, the Earth more or less goes in a circle, right? So admittedly, this is an approximate calculation because the truth of the matter is that the planets don't actually go in circles, they go in elliptical orbits with various eccentricities. And that can be derived with calculus, but not the calculus we have in this course. It really relies on this, the technique of Lagrangian mechanics. You generalize coordinates and things. It's not quite within our realm in here. So we're going to have to stick to the circular approximation, which is fine. We can do lots with that. But if we assume that the Earth travels in a circle around the sun, we can say much, right? What keeps it going in a circle is the force of gravity, right? The force of gravity. And so what we've got, yowzers, is mass of the Earth, right? Times the velocity of the Earth squared divided by its radius is equal to big G, mass of the Earth, mass of the sun, divided by what? The radius squared. Now why do I put these two things equal? What's going on here? It's going in a circle, right? And it's constant speed motion as well. All right, so the constant speed circular motion, we know that the acceleration is mv squared over r, right? The acceleration is purely centripetal. All right. So again, this is a slight okay, so let me shut up about what it's not. Okay, so then this is the force. Now, why is there the minus? It matches up, right? So it's center seeking, which is the direction we need for the centripetal acceleration. So there's no need for a minus here. The mass of the Earth is irrelevant, right? So we can cancel that. And what does that give us? It gives us that. What else should we do here? How is the radius of the Earth's orbit related to the period of the Earth's orbit? Because we're trying to find Kepler's law, which relates the period to the orbital radius, right? So the way that those two things are tied together, we need to remember that the speed is the distance traveled, which is the circumference of the orbit, divided by the period, t. What's the period for Earth's orbit? Whoa. Put that there.
1 year.
1 year. Good answer, right? So yes, the period for Earth's orbit is 1 year. And all right, let's put this in here. What we got? So we've got v squared. So I guess we've got v squared r is equal to big G times the mass of the sun. Is that right? So I multiplied r squared over there. So I've got r squared over r, which gives me r. I've got the v squared, I'm leaving it there. Cancel my mass of the Earth. Now let's put in the v squared. So that's, you got yourself 2 pi r divided by the period, quantity squared, times r is equal to G times the mass of the sun. So what do we got here? We've got r cubed divided by t squared is equal to G times the mass of the sun divided by 4 pi squared. That, my friends, is Kepler's law. It says that the cube of the planet's orbit divided by the square of its period is constant. Notice that the ratio of the cube of the orbital radius to the square of the period of the radius is independent of the mass of the Earth. So this ratio, I mean, I drew the picture for the Earth, right? And this is true if I think about, let me stick a r sub e and a t sub e, right? But this would also be equal to, for example, the radius of Jupiter cubed divided by, you know, the period for Jupiter squared, right? By the way, we have a name for the mean orbital radius of the Earth. What's that called? Radius of the Earth equals to? This actually defines a system of an astronomical measure. What's this called? 1.0 what's? Astronomical units. Very good. So 1.0 AU, astronomical units. So here's an example we could do. If we knew if we knew, for example, either the radius or the period of Jupiter's orbit, we could figure out whatever we're missing. It turns out that you can measure Jupiter's mean orbital radius is about 5.20 astronomical units. So, What example am I on here? Example 3. So example 3, the radius of Jupiter is equal to 5.20 astronomical units, right? Find how long a Jupiter year is. How long does it take for Jupiter to complete one revolution around the sun, right? So we can work that out. We use this proportion. And so we've got the time for Jupiter squared is equal to the radius, goodness gracious, the radius of Earth cubed divided by the radius of Jupiter cubed times the period of Earth squared. So I just solved this ratio for the time for Jupiter, period for Jupiter squared. And as such, this gives us that the period of Jupiter is equal to the square root, right, of 1.0 cubed divided by 5.2 cubed. And then we got TE, right? Time for the period of the Earth. So the period for the Earth orbit, of course, is 1 year, right? TE is 1 year here. And so we just have to work that out. I think I did something backwards. Uno momento, por favor. Oh yeah, I got it flipped. I got it all turned over, don't I? What should I have? See this? If I solve this for TJ, what do I get? I get the Jupiter should be up top, the Earth should be downstairs, right? My bad. I was like, what? I'm about to get a number smaller than an Earth year. That would be weird. Let's see here. So where was I? 5.2 cubed divided by 1.0. 1.0 cubed is dumb, but there it is. So what's the square root of 5.2 cubed? It's about the square root of... Oh, goodness gracious. Let's work it out. 5.2 cubit. That gives me about 140.6. Square root that thing. I get 11.86. 11.86 years. And of course we're talking about Earth years, right? Let it be our convention that whenever we speak of years, we're talking about Earth years, okay? Otherwise I will say Mars year or Jupiter year. But 1 Jupiter year is 11.86 Earth years. Yeah? So, notice that this derivation doesn't just hold for the motion of the Earth around the Sun. It equally well applies to the motion, for example, of the Moon around the Earth, right? Or other satellites. So a satellite is something that's held in motion by the force of gravity. So the way to think about this is the Earth is always falling around the Sun, right? It just keeps falling and falling and falling. Oh no. Oh. So it begins. All right, let's see here. Trying to decide what I should erase. Well, you guys don't like this, so let me erase this. Oh man, I didn't want to erase that. So let's talk about potential energy just a little bit here. So we have the force of gravity is minus gmm. And I'm going to put the one of the masses at the origin just to make life easy. R squared r hat. All right. So if I want to make that equal to, like, minus the gradient of some potential energy function, all right, since the motion, since the force is just in the radial direction, that calculus here works out real nice. It's just minus du dr r hat. All right? So the potential energy for gravity should just be a function of the distance from the origin if we're talking about the potential energy due to, let's say, the mass big M. All right? So you guys tell me. We've got du dr is equal to g m m over r squared. What's u equal to? Notice the minuses cancel. Do I have to do everything? Come on, you guys have had calculus. Help me out. The g, the big M, the little m, they're constants. We're just integrating with respect to r. What do we get? U equal to what? How about this? Minus gm, big M, divided by r. If you differentiate that, you get minus 1 over r squared. Minus minus gives you a plus. Yay, we got it. All right, now plus a what? Plus a constant, right? So we could, we could add a constant over here like that. So here's the convention which is typically used. So we can set u sub 0 equals to 0 to make u of r go to 0 as r goes to infinity. Okay? Did you guys notice anything like peculiar about this formula for potential energy? So like let's just let me draw a picture. What's going on here? We've got some mass, right? Big M. And I'm talking about the potential energy for a little mass out here, distance r away. That's the potential energy for little m due to big M. That's how much energy is stored. How do we get the energy back? You just let the little mass go, right? And it just, yeah, go ahead.
If you go all the way around, then the gravity takes a point in the opposite direction, it's technically back again, and then as you orbit, it just stays.
Oh, but as we orbit in a circle, the potential energy is constant. R is a scalar here. There's no sense of direction. It's just the distance from the origin. So like the potential energy here is the same as the potential energy up here, is the same as the potential energy over here, and so forth. That was supposed to be a circle. All the same radius, Energy is a scalar. There's no direction with energy. So like the question I was begging is like, what happens? How do you get the potential energy back, right? I mean, I've been illustrating it just like this, right? Just let it go, and it drops, the radius lowers, and you go from more potential energy to to less. What happens with this formula if r equals to 0? Yeah, oops. But do we get to r equals to 0? We don't. Is actually all of the mass of the Earth at radius 0? No. So if we were to go through some careful arguments, The actual story is, I better make myself some more room here. Let me do it over here. So let me try to explain to you guys what the there's some subtle things going on here. So if we assume, let's see here, this is the force, this is the radius, all right? And let's say right here is the radius of the Earth. So, goodness gracious, if you can imagine, if you're here at radius, let's say r, and r is less than the radius of the Earth, right? Then only the mass inside that radius is pulling you towards the center. If you study all of the mass outside of that radius, it's pulling away, but it's pulling away in a symmetrical fashion such that it all zeroes out. So this can be made more precise by mathematics that I don't have at my disposal here, but in a nutshell, the force of gravity on excuse me, at distance r is just based on how much mass of the Earth is inside radius r. So if you assume that the Earth is a big chunk of cheese of uniform density, what's the mass here? What's the mass inside that little bit? What's the mass inside radius r? We can use a proportionality, right? It's proportional to the volume divided by the total volume. So the volume inside there, 4/3 pi little r cubed, divided by 4/3 pi radius of the Earth cubed, right? So that's the volume inside radius r relative to the total volume. That's the proportion of volume that you have inside a radius r sphere, inside the Earth. So I multiply that fraction times the mass of the Earth. That gives me the mass inside there. So what's the force of gravity? What's the force of gravity here at distance r from the center of the Earth? So the force of gravity is equal to, and I have to kind of imagine a hypothetical. By the way, the right way to think about this little mass is it's a tiny little test mass. So, I mean, whatever, here's the little m, all right? So the force on that little mass is g little mass, mass inside radius r, divided by radius r squared. What's that work out to? Well, the 4 pi over 3, they'd be canceling. And so you just got yourself a g little m r cubed divided by r squared, radius of the Earth cubed. Some things cancel, and of course I'm just talking about the magnitude. The direction is center seeking, but goodness gracious. So that's g m r divided by the radius of the Earth cubed. This is what it has to be for a couple reasons. Number one, the force of gravity is 0 at the center of the Earth, because at the center of the Earth is symmetrically pulling on you in every different direction all at once. So the 0 force of gravity at the center of the Earth. So the formula has to go to 0 for r equal to 0. This does. The other thing is it has to go to gm. So here is a picture of the force. It goes from 0 at 0 radius up to its maximum value of g m mass of the Earth divided by the radius of the Earth squared at the surface. Then what happens? That's the biggest the force of gravity ever gets on the Earth is right where we are. Unless you could go to like, well, no. I mean, it's right where we are. I'm pretty sure. Maybe sea level would be a little bit better, right? If you could be at the mean orbital radius, that should be where the maximum gravity happens, unless you could somehow find like a large deposit of mass somewhere that would amp it up a bit, right? So, sorry guys. There's a silver lining to this. It's looking like I'm going to have a cough for graduation, which means I don't have to go. So, so if over the next few weeks it seems like sometimes my cough is manufactured, you know, just understand. Maybe for a good cause. Let's see here. So past the radius of the Earth, it drops off as an inverse square, right? But inside the radius of the Earth, the gravity drops linearly to 0. All right? What does the potential energy look like? So you got to think about this. The potential energy function, so what I'm trying to tell you is this formula over here, this is really only legit where? For a radius greater than or equal to the radius of the Earth. As we apply this concept to the Earth system, the potential energy being gm minus gmm over r, it's only appropriate past the radius of the Earth. Inside the radius of the Earth, something else happens, right? If you want, come on. Can you guys tell me what would the potential energy be inside the Earth? It wouldn't be reciprocal anymore. What would it be? Can I erase this? I better not. I better keep. I'm going to keep that. So, to find the potential energy inside the Earth, we should set this equal to, of course, it's center seeking, right? So for the reasons that we went through before, this would be equal to du dr, because I canceled out the minus, right? Just like we did in the other one. So that means potential energy inside the Earth as a function of radius be gm over radius of the Earth cubed times r squared over 2, because the integral of r is r squared over 2. So it's quadratic. And now we have to add a constant though, right? You know, plus some constant. And I don't know, what do you guys think that constant should be? I'll call it C1. What is the situation here? Ay, ay, ay. So if I plot it up here, here's r, here's radius of the Earth, right? We have what's the potential energy at the radius of the Earth? If we set the potential to be 0 at infinity, it is minus gm minus gm mass of the Earth divided by radius of the Earth, right? And then it goes to 0 like so, right? So that's this purple that I just drew is where u is equal to minus gm m of the Earth divided by r. But inside the radius of the Earth, something else happens, right? So it's a quadratic. Unless I made a mistake, I think it's a positive quadratic, right? I mean, I have minus gmm over r squared is equal to minus du dr. I think I've done that correctly. So that should be 1/2. So how do you, in order to match these up, I mean, if my C1 was 0, it'd be up here, right? So if we want to make these match up, we're going to have to make C1 negative. Yeah? It's not immediately obvious to me what I should make C1 be. But And this doesn't really, I don't think we'll ever need this, guys, so I'm just kind of getting into the weeds here a bit. But we can make a value for C1 such that the, right there, so to find C1, we would like to have, it's whatever it takes to solve this. Gm, radius of the Earth, oh, I'm dummy. What happens when we put r equal to the radius of the Earth in the formula for the square? The cube and the square cancel, and we just get what? We just get G, M. So I've lost my mass of the Earth here. Mass of the Earth. Mass of the Earth. These were all supposed to have mass of the Earth, right? So G, mass of the Earth, Gm, mass of the Earth, divided by 2 Gm, mass of the Earth, divided by 2 times the radius of the Earth. That's this formula. When I plug in r equals to try to glue the cases together right here, I should like for the potential energy to be continuous. If the potential energy is not continuous, that means that there's some sort of like force right at the surface. You know, there's no such thing. There's no like, anyway. So plus C1 is equal to minus Gm me over Re, right? So you just solve that. You can solve that for C1. What do you get? Oh. We get so if I subtract that over to the other side, it looks like I'm going to have like 3 minus, if I'm not doing something wrong, like minus 3 GMM over 2 RE. Anyway, enough of this. So let me ask a practical question. Suppose, I gotta find a spot to write. So suppose you have, you're on the surface of the Earth, right? And Mr. Top Hat's standing here, and he's got a mass, right? And there's the mass with velocity v naught upward. Does the mass come back? No, so I'm ignoring, let's say, what's the word? Ignoring orbital motion and so forth. Like just, if you can imagine the Earth just sitting still, only thinking about the gravitation of Earth itself, what happens to the mass, So we're essentially throwing it from radius of the Earth to start with, right? So conservation of energy for the mass that's thrown up looks like this. Minus G m, mass of the Earth, divided by the radius of the Earth. That's its initial, what? Potential energy, yeah? So you're like, wait, I thought potential energy was m little gh, right? Well, no longer. This is the new potential energy. Gmm minus gmm over r is potential energy. When we imagine motion that involves more than just surface level dynamics. So this is the potential energy due to gravity we have to deal with for these kinds of questions. And so then I, of course, have plus 1/2 little m v naught squared, right? And the question is, so like, what would it take for the ball to come up, right? And, oh, goodness gracious. I'm trying to think of the right answer here. So, So how high does the mass go is my question. right? Like, we could solve this for what? Minus g m mass of the Earth divided by the top radius it gets to, right? When does that equation have a solution? I know we're out of time for today, but we can answer this question together. Here, let me ask you a question. If my kinetic energy was larger than this value, what would that make this? This would make this a positive number. Does this have a solution? If the left-hand side is positive, think about this. There is no way to solve the right-hand side. This is the mathematical evidence that if you have more kinetic energy than that amount, the ball never comes back. It just keeps going. It is unbound. It is gravitationally unbound. It has what's called escape velocity. Now, the good news is, it's relatively hard to throw stuff that fast. So we don't usually lose balls according to this, but we'll try to work out what that speed actually is like in a future lecture. I just wanted to point out to you that that's an issue now. So anyway, I'll see you guys. We have many more examples to do on gravity. We are just at the start of all this, guys.